5G was engineered to solve three contradictory requirements within a single infrastructure. Beyond increasing consumer bandwidth, the protocol architecture had to simultaneously handle massive device density and near-zero latency reliability. The first requirement is Ultra-Reliable Low-Latency Communication, or URLLC. Certain critical applications, like remote robotic surgeries, demand end-to-end data latency of less than 1 millisecond. Any packet loss or delay here risks systemic failure, meaning the network must prioritize immediate data transmission above all else. Simultaneously, the network must support massive machine-type communication, or mMTC. In dense urban environments, autonomous vehicles and ground sensors create up to 1 million separate device connections per square kilometer. These devices transmit tiny bursts of data, often relying on batteries that must last for years without maintenance. This creates a severe engineering paradox. A network optimized to guarantee instantaneous heavy data transfer for URLLC is incompatible with the traffic patterns of a massive swarm of tiny sporadic IoT data bursts. Traditional methods of handling network traffic would instantly bottleneck. Resolving this tension required a complete teardown and redesign of the telecommunications architecture, moving away from simple hardware upgrades into a redesign of how communication protocols operate. This rebuild is best understood through the Open Systems Interconnection, or OSI, model. 5G's primary innovations occurred by dismantling the rules governing the bottom three layers of this framework: the physical, data link, and network layers. Historically, the bottom tier, the physical layer, was treated as a static pipe, responsible only for the transmission of raw bit streams over a physical medium, like radio waves. Above that, the data link layer acted as a traffic cop. It coordinated how devices accessed that physical medium, ensuring data packets were framed and transmitted without colliding. And at the top of this foundational trio, the network layer used fixed hardware to handle the routing and forwarding of those data packets across the core network. By replacing the fixed operations of these three layers with software-defined protocols, engineers achieved network slicing. This allows a single physical infrastructure to be partitioned into independent virtual networks, each optimized for entirely different tasks. Starting at the bottom with the physical layer, 5G introduces the new radio, or NR, interface. This air interface is tasked with transmitting across a massive spectrum range, spanning from sub-1 GHz bands up to high-frequency millimeter waves above 24 GHz. This diagram shows how NR maximizes that spectrum using orthogonal frequency division multiplexing, or OFDM. It divides the available radio spectrum into multiple closely spaced subcarriers, represented here as individual blocks on a grid of time and frequency. In legacy 4G networks, the spacing between these subcarriers was static. The grid remained uniform, regardless of whether the signal was traveling across a dense city block or a 50-mile rural highway. 5G breaks this rigidity through a physical layer innovation called scalable numerology. This allows the network to dynamically shift the subcarrier spacing on the fly, altering the structure of the waveform to match specific deployment needs. When broad rural coverage is required, the network shrinks the subcarrier spacing. This tight numerology optimizes the lower frequency bands to push signals through physical obstacles and across vast distances without degrading. Conversely, in a dense urban environment requiring massive data capacity, the spacing expands. This wider numerology allows high-frequency millimeter waves to push enormous amounts of data over short distances with almost zero latency. This adaptive spacing is compounded by 256 QAM modulation, which dictates how data is encoded. By transmitting 8 bits of data per individual symbol, the physical layer increases total throughput. Base stations also deploy massive MIMO technology, using a large array of antennas to spatially multiplex signals, serving dozens of distinct users simultaneously on the exact same frequency block. Through these combined protocols, the 5G physical layer operates as a malleable waveform foundation, capable of reconfiguring itself to support contradictory demands. Moving up the stack to the data link layer, we reach the medium access control, or MAC, sublayer. This is where the network dictates how devices actually get permission to use those radio waves. Traditional cellular networks operate on a strict request and grant protocol. A device must send a signal asking for permission to transmit, wait for an open frequency slot, and then send its data. While orderly, this protocol creates a failure state for massive machine-type communication. If 1 million IoT sensors in a single square kilometer suddenly need to transmit a temperature update, the MAC sublayer would instantly collapse under the volume of access requests. To prevent this gridlock, 5G introduces grant-free access. This protocol allows massive swarms of IoT devices to bypass the request queue entirely, transmitting their short, sporadic bursts of data straight to the network without waiting for permission. By removing the need to wait for a network response, grant-free access allows remote sensors to immediately return to a low-power sleep state, preserving battery life for long-term field operation. However, while thousands of sensors are transmitting grant-free bursts, the MAC layer must simultaneously handle critical URLLC traffic, like our robotic surgical data, which cannot wait for random traffic windows to clear. To manage this, the MAC sublayer utilizes dynamic scheduling algorithms. It actively identifies latency-sensitive URLLC packets and instantly prioritizes them, pausing or deprioritizing the massive IoT traffic in real time to clear a path. By applying distinct access rules based on the exact nature of the device requesting connection, the data link layer maintains order over millions of concurrent connections without gridlocking the network. The physical waves have been optimized and access has been granted. Now, the data reaches the highest structural level of our trio, the network layer, managed by 5G's next-generation core. In legacy architectures, the core network relied heavily on physical hardware components. Functions like routing data and managing user sessions were bound to specific server racks, making upgrades and scaling slow. 5G solves this bottleneck by implementing a service-based architecture. In this design, network functions are decoupled from physical hardware. They are virtualized into independent software services that can be deployed instantly anywhere in the network. These services are split into specific microtasks. The Access and Mobility Management function, or AMF, handles the tracking and verification of user equipment as devices move through different cell zones. Meanwhile, the Session Management function, or SMF, oversees the establishment and teardown of data sessions between those devices and the core network. And the User Plane function, or UPF, is isolated specifically to handle the heavy lifting of routing and forwarding the actual data packets to their final destination. Because these functions exist as modular software, operators can instantiate them dynamically to create network slices. The physical infrastructure is partitioned into multiple isolated virtual networks running parallel to each other. To ensure these slices operate correctly, the core utilizes a Quality of Service Class Identifier, or QCI. This numerical value dictates strict priority rules across the slice. One slice is given a high QCI to guarantee sub-millisecond latency for autonomous cars, while an adjacent slice receives a lower QCI to maximize efficiency for agricultural sensors. This service-based architecture takes a single physical deployment of antennas and servers and allows it to operate as dozens of bespoke, highly specialized networks simultaneously. We can now trace a data packet from its generation, modulated over perfectly spaced physical radio waves, bypassing access queues through a grant-free data link, and routing cleanly into an isolated software slice managed by the service-based architecture. But this flexibility introduces a severe operational burden. To maintain this multi-layered environment, network operators have to manually define and adjust the parameters for thousands of distinct quality of service flows. When these parameters are manually configured, they become static profiles. If real-world traffic behaves unpredictably, such as a localized surge of smart city data during a major event, those static parameters cannot adjust fast enough, leading to packet loss. The complexity of monitoring 1 million devices per square kilometer, prioritizing life-saving URLLC data, and orchestrating virtualized core functions is beyond the capacity of human network engineers. The 5G structural architecture successfully created a capable network foundation, but its management paradigm is reaching a hard mathematical limit. This operational threshold is the catalyst for the next evolutionary phase of connectivity, defined as the Beyond 5G, or B5G, framework. To break the human management limit, B5G deeply integrates artificial intelligence into the core infrastructure to drive predictive, adaptive quality of service management. Instead of relying on static profiles, machine learning algorithms continuously analyze vast amounts of live network telemetry. By identifying traffic patterns, the AI can proactively shift bandwidth, dynamically resizing network slices and adjusting access priorities just milliseconds before localized congestion occurs. This intelligence is paired with the expansion of edge computing. By moving processing power out of the centralized core and directly into the local base stations, B5G physically eliminates the round-trip transmission latency for edge devices, allowing critical applications to execute immediate logic locally. The structural protocols created by 5G rebuilt the entire OSI stack to handle massive complexity. By automating that foundation with AI and localizing processing at the edge, beyond 5G networks convert the 5G foundation into an autonomous, unified communication infrastructure.